Hello everyone, welcome to this YouTube video. We will today be discussing on upthrust. So upthrust is obviously an upward force which rises due to the pressure difference. The pressure difference will cause an upthrust to act on the body. Let's suspend a mass with a Newton meter. So this is just a Newton meter. It is also suspended freely, and with this Newton meter we have attached a block, suppose. So this block is attached at the end of this Newton meter, and we are going to find some reading on this Newton meter. We are going to find some reading on this Newton meter. So whatever reading we get in the Newton meter, it is actually representing the weight of this block, isn't it? So the weight of the block, which is acting vertically downward, it is suspended at this particular position. So it is neither going down anymore or going up. It means the tension which is acting in the upward direction is as much as the weight of the block, and this is why the block is in equilibrium at this position. So this tension value from this Newton meter gives us the weight of this block. Now I submerge this block in a water tub, say for an example. If I submerged the object in this water tub, will the tension value remain the same? No. The tension value now will be some less than weight. So this block is now submerged in water. So doesn't matter it is fully submerged or partially submerged. So say for an example, we placed it in water tub and we see some part of the wooden block to be submerged and some part of the wooden block to be above the water. Well, this is the case what we have. So T equals to W, that is what we have seen earlier when the wooden block was freely suspended without any water tub here. And now when I placed the water tub and allowed the mass, the block, to submerge in this water, this is what we see. Some part of the wooden block, the block is into the water and some part is above the water. So we see the tension value right here to decrease. Now what happens, which is why the tension value decreases? So it is the upthrust which is acting on this block in the upward direction due to the pressure difference, and it is acting on the block. So this upthrust now is going to be added up with the tension, which is lower than the actual weight of the object. This is now going to be equal to the weight of the object. So at first, when it was not submerged in water, whatever tension value we got, we called it to be the weight. And now when it is in water, we observe the tension value to decrease from its initial value. So we reason for this, that why did this value decrease? It is because of this upthrust, which is now acting on this object by the pressure difference when it is submerged in this liquid. So upthrust is the upward force that is acting due to pressure difference. That is the important thing here to remember. It is the pressure difference that causes the upthrust to act on the object. Well, so we would like to understand that if the object is submerged in water, say for an example, then how we can calculate the upthrust, what upthrust becomes equal to. So for the simplicity of our calculation, we consider this to be a uniform shaped object which is completely immersed into water, completely It is immersed into water. If it is immersed into water completely, then top of the surface, top surface of this block is some h1 depth below the water surface. It is h1, and this bottom surface of the block is some h2, depth below the water surface. So we are measuring this h1 and h2 from the water surface. Top one is at h1 depth, bottom one is at h2 depth. So the top one is experiencing a force which is acting downward, bottom one experiencing a force upward. And these two forces on the top and the bottom are not same, because here the force is pressure times area. So if we consider this to be and as we considered the uniform shaped object having a uniform cross-sectional area, so area of the top surface and area of the bottom surface is same. So pressure on top is H1 rho g. This is the pressure equation due to the liquid. Pressure is H rho g. So here H is H1 because it is H1 depth below the water surface, multiplied with the area of the cross section. So this is the force that is acting on the top of the surface, which is acting downward. It is acting downward, remember, acting downward. Now what is the pressure on bottom? And hence what is going to be the force on bottom? So force on bottom is pressure on bottom times its area. It is H2 rho g A, and this is acting in the upward direction. Okay, water here will be exerting this force in the upward direction on the bottom surface. So we understood that force on bottom is greater than force on top because H2 is greater than H1. So if we want to find out the net force here, the net force is force on bottom minus force on top. Force on bottom is H2 rho g A negative force on top, which is H1 rho g A. Now we are going to do some kind of simplification. H2 minus H1 A, then rho, then g. This is how we simplified the above expression. Now H2 minus H1 is what? It is nothing but the height of this object. This is the height of this object, h. So this h, which is the height of the object, multiplied with its area of the cross section. And this rho is nothing but the density of this liquid where the object is immersed. So it is here the density of water, because I consider this to be as water. I mean, if it is water, it is water. If it is some other liquid, then you will write down the density of that liquid. For an example, it could be oil, so density of oil. So where the object is submerged. So if the object is submerged in this particular liquid, you will write down the density of that liquid only. This is multiplied with g. Now height of the object times its cross-sectional area is nothing but the volume of the object. The volume of object times the density of fluid, here it is water, times g. This is the net force, and you see this volume of the object, since the object has been fully immersed into this liquid, so volume of object is nothing but volume of the displaced water. So as the block completely immersed into this water, it will spill over or it will displace the same volume of water. so that it can occupy that particular space. So volume of object is equal to volume of displaced water. Why? It is because it is fully immersed, as fully immersed, fully immersed. If it were immersed partially, some part below water, some part above the water, then we could not say, we would not been able to say that volume of the object is equal to the volume of the displaced water. All right. So here in this case, this volume of the object is the volume of the displaced fluid, displaced water. So I wrote displaced water as d slash w times the density of water times g. So volume of this much displaced water times the density of water, isn't it the mass of displaced water? This is multiplied with g, which gives us finally the weight of displaced water. So this is basically the weight of the displaced water. Why the weight? I mean, why the water displaced here? It is because when the object is immersed in the fluid, then it will be displacing its equal amount of volume, how much space it occupied in that particular fluid, that much volume of fluid it will displace. So here this force on bottom is greater than force on top. So force on bottom is acting in the upward direction. So this net force is nothing but the upthrust, which is always in the upward direction, because force on bottom is acting in the upward direction. So resultant force acts in the upward direction. So resultant force acts in the upward direction, and here the upthrust expression that we got as the weight of the displaced fluid, this is Archimedes' principle. Archimedes said that weight of any displaced fluid is equal to the upthrust acting on that object when the object is in that fluid. Now, as I said over and over again, fluid. So what is fluid? Fluid means anything that can flow, and it could be gas, it could be liquid, it could be liquid. So getting back to the same problem or same situation that we started with, when the mass was initially just attached at the end of the Newton meter, and we said that just tension is equal to weight, and that time we did not consider any kind of upthrust, right? We said that this is the Newton meter. This Newton meter, at the end of it, a wooden block is attached, and it is, this whole system is freely suspended. So whatever the tension we get from this Newton meter, we told that tension to be equal to the weight, the downward force and upward force. So here we did not consider any kind of upthrust. Why didn't we consider any upthrust? It is also fluid where the object is, because air is also a fluid. But here we did not consider the upthrust. Upthrust due to air is negligible. Upthrust due to air is negligible. Why is it negligible? It is negligible because the density of air is much, much lower than density of any other liquid you can consider. Density of air is much, much less than here the density of water, the water that we considered in this situation. We could not ignore this density of water when something is immersed in water, partially or fully. But when something is in air, then we can easily ignore this upthrust, because this upthrust value is very, very, very less, very small. For the smaller object like this wooden block, it is again tiny. You cannot compare this upthrust with the tension or weight of the object that is acting. So this is why we do not consider the upthrust. It is negligible, that is why. But some finite upthrust still is acting on the object when it is in air as well. Okay, but the effect is negligible. But here we cannot say this effect is negligible. All right. And at whatever situation the object is, once it is immersed in the fluid, if we consider this to be the ship or boat which is floating on the top of the surface, some part of the boat is immersed, some part of the boat sinks below the water, rest of the part of the boat is above the water, so it is floating at this situation. Ship is also like this. Once we consider the submarine, this submarine is deep in the ocean. So this submarine deep in the ocean, so when it is in the ocean, again the submarine sometimes tries to maintain a constant depth. So at whatever position the object is, it is floating like this or it is fully immersed and maintaining a constant depth under the ocean, doesn't matter. The flotation principle will be followed by the downward force weight equals to the upward force upthrust, as long as the object is maintaining a constant vertical position. It might be floating above the water surface, some part sinks below, the other part is above the water surface, or else if we consider the submarine, if we consider the scuba diver who is swimming deep in the ocean, as long as he is maintaining or she is maintaining the constant depth, that means the vertical position is constant, it is neither going up or going down, so upward force and downward force, they must be equal. So weight equals to upthrust. In that case, we will be considering. And this is the situation where we see that when the ice block is taken in water, that 90%, 11 12th of ice is below the water and 1/12 or almost 10% is above the water. So once it is floating like this, whatever weight the ice block has is equal to the upthrust that is acting on it. So weight equals to upthrust. This is the principle of flotation or flotation principle that we can say. Means the object either partially submerged or fully submerged, as long as it is in the same vertical position, the upward force equals to downward force. The upward force is upthrust, the downward force is weight. So these are the cases of upthrust, and lots of examples are there. The aircrafts are flying, maintaining a constant altitude when flies. It is because of this upthrust. We call this upthrust to be aerodynamic lift. We call this to be aerodynamic lift. Here you can ask the question that aircraft, when it is flying, it is flying through air. As we said, the density of air is much, much less than density of any liquid concerned. So upthrust is negligible. So why we consider the upthrust for this aircraft? Well, the aircraft, you see that there are rotor blades attached or rotor blades installed in the wings of the aircraft. These used to drives away the air molecules. So on the top of the aircraft, on the top of the wings, and at the bottom, there is a pressure difference. Somewhere there are more air molecules. That means on the bottom of the wing, air molecules are greater compared to on the top of it, as the air molecules are driven away because of the fast moving rotor fan attached on the two wings. This is why the pressure exerted by the molecules down the wing is greater than the pressure of the molecules on the top of the wing. And here the pressure difference causes an upward force to be experienced by this aircraft. And this is what we call as aerodynamic lift. This aerodynamic lift helps the aircraft to maintain its particular altitude when in flight. Another example is hot air balloon. Once the hot air balloon starts rising up, what does it do? It burns the gas, and the density of the air goes down. The less dense air, you must know, the less dense air rises up. It goes in the upper direction. In the upward direction. So when hot air balloon is to leave the ground and lift up, you see that there is a chamber in the hot air balloon where there is a setup of fire. So a certain amount of gas is being burnt right there. The density of the gas goes down, and this rises up. This is going to produce an upward force on this entire hot air balloon, which is greater than its weight. So the upward force greater than its weight causes it to rise up. And as it keeps on moving, if we want to now, when in flight, when in air, if we want to maintain the constant particular altitude, so we will be adjusting the amount of gas to be burnt or to be released. So we are basically adjusting the upthrust acting on the hot air balloon to maintain the constant depth, or to maintain the, not depth, altitude, to maintain the constant altitude, or to maintain any particular altitude. Should I go higher, or should I descend, or should I maintain a particular depth? I'll be adjusting the upthrust by burning the gas. So these are the examples of upthrust. I hope you understood what is actually the upthrust is. It is just the pressure difference. You see again the helicopter. So how does it fly? How it hovers? So once the blades are started rotating, these are again producing immense pressure difference, wiping away the air molecules from the top, and ultimately at the bottom air molecules are greater, number of the air molecules, so they are exerting more pressure and hence more force on the blades, and this is how it hovers, it flies. So upthrust is the pressure difference, which is why an object experiences an upward force. All right. Sometimes you might get a question where it is asked that why the upthrust has not been considered. Then you will have to compare this upthrust value with the weight, with the tension, with the drag force. The forces that are concerned in that particular question. And since this upthrust mostly in air, the density of air, because while calculating the upthrust, we consider the density not of the object, rather the density of the fluid where the object is. So since density of air is much less than density of anything else, So the upthrust is going to be negligible compared to the other forces concerned. All right. So if you understood it, let me know. If you don't understand this, then also let me know so that I can particularly pinpoint the issue. And there are some questions on upthrust, so probably I'll be addressing those questions in the next video. All right, so thank you, sir. May God bless you.